All right, welcome back. Let's talk more about object-oriented programming. More oop, less oof. And we'll talk about a new concept called ADTs, which is short for abstract data types. So let's get right on into it. How are we doing with Vim? Did we all do Vim Tutor? Are we all happy? Are we stuck in Nano right now? Definitely do Vim Tutor if you can remember. It will save you so much pain throughout the semester. But a lot of people eventually they graduate to a graphical code editor, and most of the world likes to use Visual Studio Code right now, especially the students. So that's probably the next place to go. But I highly recommend starting with Vim. All right, and then learning Vim with the Vim tutor. I'd be happy to help. Okay. Before we get into new things today, I just want to remind you of some of the things we talked about last time because some things were a little weird. So like let's pretend we've made a class. So we've made a class and like we're making an object of our class, and we need to remember what's going on when I instantiate this. When I make a brand new object of my class called counter and I call one of its constructors, like what in the world happens? Here's a list. All right. This is what happens when an object is born in the order that that these things happen. So the very first step, of course, is you say I want a counter object called myC. You have to make memory, right? The compiler is going to emit some code that's going to run, and the very first thing that happens is we need to make space in our memory for this program for this object. However many bytes a counter needs is going to get allocated on a place called the stack, if you remember that, and then it's time for the constructor to be called. So after memory gets allocated, then whatever constructor you're calling is going to be, we're going to jump to that code and it's going to run. So this is a parameterized constructor call. So we're jumping to that one and 42 is being passed along. It's going to use it. All right. But before we hit the body of that constructor, right, remember that there's an initializer list potentially. If there is an initializer list, all of the member variables mentioned in it are going to be constructed in the way that we ask. All right, so go back to last time if you need a refresher on what initializer lists are, but it's a little colon, sad face looking thing. It's a bunch of constructor calls before the body of the constructor. And then any member variables that you didn't mention in the initializer list that are just like non-primitive, and by primitive I mean like an int, a bool, a double, a char, just things that are built into C++. That's not like structs or classes, not objects, but just like basic things, primitive types. So anything that's not primitive, like if you have a vector that's a member variable, and you didn't mention it in your initializer list, then it gets default constructed. So for example, if you had a vector member variable, you didn't talk about it in your initializer list, then it becomes empty because the default constructor on a vector just makes an empty vector, right? Same with a string. If you had a string as a member variable, that the default constructor for a string, it makes the string empty, right? So all that will happen. And then any primitive type member variables are just set to complete garbage, whatever is in memory at the time. And then finally, we start running the body of whichever constructor we asked about. If we didn't say like 42 right here, then we're hitting the default constructor, right? But by adding these parentheses, we're calling a constructor, calling a parameterized constructor that actually took something, that took this int, okay? So I think that's what I wanted to say. Any additional things? A lot of the time you can get it all done in the initializer list, but sometimes there's some more actual code that needs to be run, and that is the last thing that happens, the body of that constructor, okay? So yeah, there's that. And now let's get into the new stuff. But before we talk about things that are brand new, I do want to talk about another thing that I just kind of mentioned as I was going over the lab last time. So I want to talk about the string stream type, and that all lives in the S-stream header. So let's go there, okay? Because we're going to need that. You're going to need to understand that to make your own tests for our lab 0, right? So that S-stream lives right here. It's in the input-output section of this website. It's called cplus.com. It's a very useful website. So please go there. And a string stream is this one. It inherits, if you remember that word from CSCI 40, it inherits from both iStream and OStream, which means you can put stuff into it. That is which way? That's this one. You can put stuff into it, and you can also extract things out of it. It's kind of your own personal C in and C out, and it lets you build up a string secretly. All right, so a good thing to do when you ever go to, like, you have a new class that you're learning. You can click on maybe the constructor usually, the constructor for string streams. If you scroll down, it gives you a nice little example of like, okay, here's somebody making a string stream. They're putting stuff into it. Looks like they're able to extract from it and do stuff like that. All right. but let me also give you my own explanation of what a string stream is. All right, so it lives in the S stream header, but it's all spelled out when we use it. It's called string stream. It's just like your own personal CIN or COut. So we looked at the documentation. You can also scroll through it some more. There's more things. Something that's useful is once you've built up a string, you've put a bunch of things in your string stream object. You can get out the string that you've built up by saying .stir, and that is somewhere here. .stir, that lets you get the thing that you've put into it. So it gives you back a string, okay? It gives you back the string that you've put into it. And this is kind of a weird example, but you click through enough of these, you get used to it. So let me show you an example of building up a string with a string stream. So let me make a new file. Let's call it, I guess, string streams.cvp. And I want to make a string stream object, so I'll include the S stream header where that lives. Okay, and so string stream, you can give it, you call it X, call it whatever you want. I'll call it SS, like the example in the code did on the website. And kind of the idea of a string stream is you're building up a string by kind of pretending it's cout or a file for a second. All right, so you can put stuff inside the string stream. Anything that overloads that output operator, right, that we talked about, it's fine. It'll work out. It'll put something in there as a string. So you just kind of pretending it's cout or a file. And so you can be like, hey, string stream 42, put 42 in there. And it's going to put it as a string. Remember, this is just an int, but it will always convert it to a string. 42 in a space. It's like I'm printing to, even though there will be no output. It's being placed inside of like a secret string, okay? And then you can give it whatever you want. Give it a string, and then another space. Give it a double. Anything that has that output operator overloaded for it, then it'll just essentially print to that string stream. And so now you've built up a string inside of SS. SS is holding, can you kind of imagine, if I were to ask for ss.stir right now, it would give back to me 42 as a bunch of characters, right? 42, then space, then blah, then space, then 3.14. That's just a bunch of digit characters, and then the new line. So that's what we've put into SS, okay? And so for the test in lab 0, that's kind of all we need this for. But you can also extract things. You can also, it kind of works as a CIN as well. You can extract from the string that you've built. So you can say, hey, I know that the first thing in SS is a number, so I can read into that, read into an int from that, like SS, read into the X member variable. Then you can read into a string next to get the blah out. So that totally works as you would expect somebody typing it into, like over CIN. I can print out the X. And then, yeah, it's always, you can get the entire string that you built up, even if you just read a piece of it with this line. I didn't mess with the string that's deep down in there. I've just like moved over it so that the next thing I read would be blah at that point. But I have not deleted the 42 by reading it, by extracting it, okay? So you can always get the entire string you've built up. I'll say built up string with .stir. And that's kind of all we really need string streams for right now. So I'll say cout ss.stir, and I won't say a new line because it's already part of the string. Okay, and that's the main bit of the program. So I'll compile this, and I'll run it, and we should see 42, and then that entire string that we've built out, including the new line that makes the prompt for my terminal happen on the next line. So that's great. It's working. Do yell at me if you have any questions about this stuff. So that's string streams. We can build up a string, we can extract from it, and anything that has an output operator, because SS is technically an O stream, right? String streams are technically O streams, as well as I streams. That's why this one works. So it's interesting, it's fun. So please practice around with this, and that will help you with your lab. And let me know if you have questions. And now we can talk about the first data structure we care about. It's one you've already learned about. Let's talk about arrays in detail, okay? So this is what an array is. An array is just a variable we make in C++. It's something with a single name, but it holds a bunch of stuff. So this is like a definition from a textbook. It holds a bunch of things, all of the same type, but we can get to each of them with indices. So each piece of an array we call an element, And what directly accessible means, again, is we can use indices to get to a place. And it's these brackets, these square bracket operators for arrays, very similar to the .at of vectors, all right? But it's more dangerous because you can go off the end. So this is an example of making an array of 50 integers. Oops, let me fix this pen around. There we go. So here is a line that makes an array that holds 50 integers. And so by saying this line, it makes something called R that holds 50 ints, and it's got space. That's one name for 50 things. And they're from indices 0 all the way to 49. All the way to 49. That is the last index of this array. And you can change stuff. You can say R of, this is also how you get stuff out. You can say R of index 2, and let's place 42 in there. And so that goes to this thing, this box, and sets 42 into there. And you can also extract it by just saying R of 2 by itself. You can see out that. And it's more dangerous than the .at of vectors because you can totally ask about R of 50 and it won't crash the program usually. Crazy enough. You can ask about R of 50, which is supposedly right here. And C++ will happily read this memory for you, even though it's not part of R. That's very dangerous. That's very not good. That's called undefined behavior. We don't like that, but that is totally possible. Okay, so yeah, let's remember kind of what happened. So this, by the way, this kind of declaration, this is making a local variable to maybe like main or something, and that would be a stack variable. All right, so that's how we're declaring an array on the stack, and we can also, there's also some ways to initialize it. So let me show this to you. Okay, so let's see. Yeah, when you make arrays as a local variable, they live on the stack, on the runtime stack for your program. So here's an example of that, just to remind us what the stack is. So it keeps track of local variables and which functions need to return to which other functions, things that have been called that are still alive. So here's main, let's say. So main's the very first thing that gets run for our program. Here I am making an array inside of main, so it's part of main's local memory. So it's a local variable to main. And I can go mess with R as much as I want. Maybe I'll say something like R of 0, make it 1, something like that. I don't know why that's so small of a 0. Let's fix that real quick. I did it again. And now that looks like a 6. Bear with me. It's hard to write on a tablet. Equals 1. There. And then let's say I call a function foo. And then more things happen, and eventually main is over. But here's foo. Foo's like a function that's void, doesn't return anything, but goes off and does stuff. This is just a sample program that can make stuff. Another way to make an array, by the way, is you say its type, say its name, and then you just put 2 brackets, and then you can give in curly braces, just like for vectors, what you want inside of that array. So 1, 2, 3, semicolon, and that makes an array of size exactly 3. So that's nice, and it's already been initialized. That's great. Okay, so if this were my program, of course, main is the very first thing that runs, and here is a stack diagram for this program running. So the very first thing that happens on the stack is main happens. So here's a stack frame, we say, for main. This is marking that main is the first thing running. There's nothing below it on the stack, and then all of main's local memory will live here in this box. It'll be a box of boxes. So main makes an array for itself. It's a local variable, so it lives within main's stack frame. And so there's R, and it lives right there. This is main's R. I purposefully called foo's R the same name. So main calls foo right here, and so for a split second in time, there are 2 functions being called, right? Because main has more lines, and main calls foo, so the stack looks like this when foo just gets called. Okay, and now we're executing foo. What happens to foo? It makes its own R eventually, and that only has 3 things in it, 1, 2, and 3. And there's no ambiguity, there's no issues, because they're separate places in memory. This is another local variable. It's not the same as main's. Actually, if I asked about R up here, C++ wouldn't let this compile because it's like, what is R? I don't have an R. Main does, though. So that's local variables in a nutshell. And then when foo's done, it gets to its last line, needs to return back to main and continue executing in main, then foo will, we say, it pops itself off the stack, and all of its local memory goes away. All right, so that's that's the stack in a nutshell. Hopefully you've seen these kinds of diagrams before. That we're gonna see a lot more of them. So that's just the stack is a way that kind of marks this is what's really happening in memory when your program's running. It's marking function calls and returns and any local variables that belong to a function call. But when a function is finished executing, like foo, hits its closing curly brace, it needs to come back to main, then all its work is done. We can get rid of its stack frame and just have mains again. So I really should be deleting it rather than drawing a slash through it. But I want you to be able to have it as you study. So that's how this example program is going to execute. And I do want to write a little bit of code about arrays, and I think I want to do it to show you this next weird fact. So an array, weirdly enough, is secretly a pointer to its first element, which is really weird. So int r, here's an array holding 1, 2, and 3. It's a local variable. I've been drawing it just like now, up to now, like this. I've said, hey, r looks like this. There's its name. It's holding 1, 2, and 3. But really, what's going on in C++ is r is a pointer. If you just say r by itself, it's a pointer to its first element. Crazy enough. So, because really, under the hood, right, 1, 2, and 3, those are separate ints in memory, but they're contiguous. So like if r started at address 100, then this 2 must be address 104. Does that make sense? Because ints are 4 bytes long. So this has to be address 104 if this starts at 100, and that means the 3 must happen at 108, must be held there, and so on and so forth if there's more things in R. But really, just saying R by itself, I shouldn't have been drawing it like this. R by itself is really just a pointer to the very first element. So a more accurate way of drawing this would be this. R is a pointer, and it holds 100, which is the address of the first element of R. It looks like that. That's really what happens when this line gets run. I'll probably go back to drawing it the old way because it's more work this way, but this is what's really happening, all right? Which implies that you can totally do this. You can say int star p equals r, because that's just copying addresses. Copying addresses, p holds whatever r holds, which is 100, so p also holds 100. It's a pointer to an int. That one is for sure an int. That's not an issue. Isn't that weird? That's totally possible, and for this reason, because arrays are secretly just pointers, by saying r of 2 and going somewhere, I can also say p of 2. Even though p is a pointer to an int, as long as there's really an array deep down, like this will work out, and this will get both of those things, both of these pieces of syntax will give me the 3, which is really odd. Isn't that cool though? So the reason that works is because secretly, because r by itself is a pointer to the first thing, like this is all following from that logic, by asking for a piece of r, go to an element of r, please, by saying like go to r of 1, what's really happening is we're starting at r, we're doing pointer arithmetic, we're saying r, start at your starting address, and then add 1 int of space, add 1 int worth of addresses to you, and then dereference. This code is equivalent to this code. It's being translated into that second one. And that's why p of 2 is going to work just fine. It starts at whatever p is, 100, adds 2 ints of memory later, so that's 8 bytes total, 4 times 2, and it brings us to here. Isn't that so weird? It's an odd fact, and we're going to exploit that fact. But let me prove that to you, just in case you haven't seen this before. It's a weird thing. So here's an array, just like a normal array, unassuming, but secretly r, if I just say r by itself, no brackets, it's a pointer to the first element of that array. Look at that. It's an address. And it's loaded into, the program's loaded into a different place each time, so it changes every time I run the program. But r, I've told you it's the address of the first element of the array. I know another way to get to the address of the first element. R of 0 is the first element, and if I ask for its address, so I should see the same thing printed twice. And I will. No matter where that array is in memory, r by itself is secretly the address of the first element of r. All right? Which implies, all right, that if I were to dereference, I'm going to get the 1. There it is. And this syntax, like r of 1, really starts at R, goes one int later, and dereferences. Secretly, that's what's going on. Star's supposed to be over here. This, what I just said, that's equivalent to asking about R of 1. Same thing. This syntax, R of 1, is secretly being translated into this. And the +1 doesn't mean just go 1 byte later, go 1 int later. So it's turning it into 4 because it knows I'm messing with an int pointer. And so that gets me the 2. That's exactly equivalent to R of 1, weirdly enough. And that lets me copy the address of that array into a pointer for ints, and I can still ask for P of something because it'll just still be translated in this way, and it will hit the array, and it will work out. All right, so that one thing you could use this for is when you're making a function. You might have seen a few of these, especially if you've ever worked with C strings in your CSCI 40 class. Those are char stars, if you've seen that. Like if you make a sum up all the elements of an array function, you could pass the array like this. You can say bracket, bracket, but you just as easily could have said this, because you're going to pass the name of the array, which is really an int star if it's an array of ints. So both of these will be exactly the same, and they can have the same body. You can go to R of whatever you want, and it's happy. Okay? So that's interesting and weird, and I hope that made sense. Please yell at me as much as you need to about that. So this is especially useful when we're talking about the heap. So you make something on the heap, you can only talk about it in terms of pointers, right? If you say new int, what are you getting back? You're getting back the address of where that int got made on the heap. So you're getting back an int star. This works similarly for making arrays of things on the heap. If you want it, you say new int of size 3, give me an array of 3 things, you're still only getting back the address of where it began. So it's not possible to store this in something like this. That won't work. Okay, so that's the secret. So yeah, whenever you say something, whenever you want something on the heap, you're getting back a pointer to where it begins, to where that memory begins. And so this is why we needed this slide, because we're getting to the heap. All right, we want to mess with the heap a lot in this class. So let me draw for you what these lines do. So pretend you're doing a bunch of things with the int I in between making it and deleting it. The very first thing that happens is we say int star I equals new int. And so we're going to run the right side first, right, before we shove it into a variable. So new int, by saying this, we make space for an integer on this magical dynamic allocated place called the heap. That's where dynamic allocation happens. So here is the brand new int. We just made space for that by saying new int, shiny and new, glistening in the sun, and it has an address wherever that int starts in memory. Let's pretend it's address 100. Wherever that starts, we get that, and that's what's given back to us over to this side of the assignment. And int star I, anything with a name lives on the stack, unless it's like a global variable. So let's say this was like in main. So I, as a local variable, lives on the stack frame of whatever function this was defined in, and it's going to hold that 100. And the type is a pointer to this integer, right? It's a pointer to this integer. There's your I. So I is pointing to the integer that is currently set to garbage. So you'd want to set it to actually something, but that's how that works. And so if you want to mess with it, you'd say like star I equals 42 or something. And once you're done with this heap memory, you say delete, and then you give its address. So I turns into address 100, and so it's saying go to address 100 and delete whatever is there. Delete that box, and so it gets rid of that thing. Okay, so that's this line. That's making a single int on the heap. If I want to make a bunch of things on the heap, I can do pretty much the same thing, but just slightly differently. So if I want an array of ints on the heap, I say new int, and then I put brackets for how many things I want. And I could have a variable here. This could have been like an n. It can be whatever you need as the program's running. Like maybe you got the n from the user. The program does not care. C++ does not care. It can make as much memory as it needs as long as you have that memory in your computer. As long as you've got space available, it won't run out. So yeah, by saying new int of 3, that makes this. So it's making space for 3 contiguous ints on the heap. It's making an array. And so maybe like, and then there's a concept of like, where did it start in memory? It's also shiny and new. So let's do that first. It's glowing. So you say new int 3, that's the first thing that happens. We made the new int of size 3 array on the heap. And there's, it starts somewhere in memory. Can't start at 100 because we were using it here, or maybe we just deleted it. We can reuse 100, but let's pretend it goes somewhere else, like maybe 104. So that implies this is address 108, this is address 112, and again, they're all set to garbage, just like this one was originally set to garbage, but maybe we changed it. Let's see. Yeah, and then we're getting back the starting address of this array, and that's being placed into here. That's what the new int gives back, new int of 3. So it's giving back 104, and that's being placed into the int star. So int star r, it's got to be an int star. You get back a pointer always when you use heap stuff. So r gets to hold that 104. It's pointing to that thing, to the start of the memory we just asked to be made on the heap. And so that's what's going on there. And you could treat this like an array for the reasons we just talked about, because it really is an array. So r, you can be like, hey, r of 0, become 42. Oops. I'm not happy with my own handwriting. Bear with me. There we go. R of 0, become 42, please. And so that'll do this, right? We'll place 42 there, because this translates into like go to r plus 0, dereference. It totally works out. Even though this is just a pointer, we can treat it like an array if it really is one. All right. And yeah, if you want to get rid of the array that you've made, you pass the address of where it starts to delete. So like r translates to address 104, right? It becomes 104. And so if we just said delete by itself, it would try to just delete the one int here because it was an int star and it thinks that's all there was. But we need to remind C++, if we made an array, the only new extra thing is you say delete bracket bracket to remind C++ that, hey, starting at address 104, it's not just a single int like it could have been, because these are both int stars, right? Don't just go and take a single int away. Go and remember that this was an array. Go figure out the size that you made it to be. It'll remember. It saved it somewhere. It just needs to be reminded to go look that up. So it'll go and delete the entire thing if you say delete bracket bracket. Otherwise, it thinks there's just one int there to get rid of. So that should do it. And that's how you create and get rid of and technically use single things on the heap, like a single int or an array of ints. And this could be any type. Make an array of counters if you want it on the heap, just by saying and using the syntax as you can imagine it needs to be changed. So just keep all the types in the right, I forget the right word. Make the types correct. So like change int to be counter everywhere it needs to be. Okay, that's what I'm trying to say. So yeah, that's how you mess with heap values. And so yeah, we just built on top of the ideas of arrays. All right, arrays can live on the heap. It's happy. Here's a question for you. Here's a bit of a hard question. All right, so here's some weird looking code where I'm using the heap a couple places, right? I would like you to draw what memory looks like. This is a hard question. This is a good one to come back to. Draw what you think memory looks like when this code gets run, these 3 lines. And then you can compare it with my answer. So please pause the video. Here's stack, here's heap. What's where? And please draw what memory looks like after you've run those 3 lines, and like section off the ones that are on the stack and the ones that are on the heap, which boxes are where. And then also please draw what happens when we say delete P. So we were to run that line, like draw an X like I drew here. Like what goes away? Can you do that? So please try that, and I'll show you my answer. And this will tell, this should tell you very quickly like what you need to study, all right, what you need to practice and yell at me about and ask. So yeah, give that a try. And then let me walk you through it. So here, if we say int star star p equals new int star, it's a bunch of stars everywhere, but what does this mean? What's it doing? The very first thing that happens is the right-hand side. What are we making on the heap? A new what? A new box that holds not an int, but an int star, right? Because you say new int, you're getting an int. You new int of 3, you're making an int array of size 3. You're always getting what you asked for. So this is making a box that could hold an int star, which is a weird thing to want, but it's totally possible. And so this made one box on the heap, right, that holds an int star. I'll put its type here. Like this is a box that could hold an int star. And it's brand new, set to currently to garbage. And it lives somewhere, maybe address 100, my favorite example address. And we're getting that 100 passed back to us and placing it into P. And the types are correct because P is going to hold the 100. This is P. Lives on the stack. Anything with a name lives on the stack, right? And then it's going to point here And if we want to hold the address of an int star, we need an int double star, right? We want to hold the address of an int star, so it had to be an int star star. I hope that makes sense and you see that it's working out. So there's that. This is currently garbage, but we're about to change that. Do you see? Because I'm about to say star p equals new int. So the first thing that happens is we make a new int on the heap, single int, there it is. Maybe it lives at address 104. And we say, like 104 is being given back to who? Star p. Where's star p? So this is just normal p, but star p is follow this pointer, set this, which is perfect. The types check out again. So we're placing 104 right here. Does that make sense? That's star p. This is star p right here. And so this int star is pointing to this int. So the types work out again because a new int needs to go, like we're getting back the address of an int, it needs to go in an int star. It needs to hold the address of an integer. And so that line did this. It set the 104 there so we can point to this new box. It also made the box. Isn't that fun? And then star p, I think you can imagine what's about to happen. This is star p, this box. Star it one more time gets us here to a final int, that last box, and that will hold 42. Does that make sense? Yell at me as much as you need to. This was an int double star, this one. If I'm drawing the types, I need to be consistent. That was an int double star. Isn't that interesting? So hopefully you see it now if you didn't get it the first time. But that's the first step. That was question 1. And then what happens when delete p gets run? Do you see it? I'll draw that in green. So if I were to say delete p, boop, if we go back to this, and think of it in the same way, I say delete I, it's going to the thing that I is holding. It's going to that address and getting rid of that box. So if I say delete I, it's going to address 100, getting rid of the thing. If I say delete R, brackets, it's going to the thing at address 104, that's what R holds, deleting everything there if it's a contiguous array. So with that in mind, I say delete P, it's going to 100. It's going to address 100 because that's what P holds, and deleting that box. Do you see that it did not delete this one too? It's only going to delete one thing. If you say new, you always have to say delete as many times as you say new. Does that make sense? Because that's a different box. That's a different box at a different address. This one doesn't like take this one along for the ride when you delete it. It's only delete P is deleting the thing at address 100 that was made with that new call that made that thing. Okay. If I wanted to delete this, first of all, I've lost this memory. This is leaked memory now. That's not good. I should have done this in a different order. I should have deleted this one first, right? Because now there's no way to go through this thing. It doesn't exist anymore, the middle, that int star. So the first thing I should have done was delete this box. And how do I do it? I need to say delete 104 somehow. And this is what holds 104, which is star p. So I should have said delete. I'm trying to be legible. Delete star p. Do you see it? Delete star p. What star p is this box? It was holding 104 before I deleted it, right? Do this line before this line. That would have found the 104 and deleted this box. Okay, that's what needed to happen first. Otherwise, we'll leak memory, and that's not good. And so I think that's the end of this example. Do you see it? Do you yell at me as much as you need to? All right. And the reason we're talking about all this and making arrays on the heap and remembering weird syntax about arrays is because I'm going to ask you to make a vector. A vector is secretly using a dynamically allocated array on the heap. It's just been doing it for you as one of its private member variables. Okay, that's what C++ vectors are doing secretly. And then a string in C++ is also secretly, right? It's secretly a vector of characters. And so it's doing the same thing. It's dynamically allocating space on the heap for whatever characters are in your string right now. And you can get rid of some, you can push back more. That's why pushback exists on a string. Isn't that crazy? Isn't that fun? So that is the secret. And if I can prove that to you a little bit, at least, vector is a container. If you go to the documentation for vectors, it's a sequence containers representing arrays that can change in size. They use contiguous storage locations for their elements, and the size can change dynamically. And all of those words taken together mean dynamically allocated arrays on the heap. That's kind of the only way you can make that happen. Okay, I hope that makes sense. And you should want to learn this now, because I'm going to eventually ask you to make your own vectors. All right, That's going to be one of your labs. So that's pretty nice. And I want to talk to you about how to build that kind of thing, how to build a vector out of dynamically allocated arrays, and like how to do that nitty-gritty stuff. All right. And I also want to talk about vectors from a higher level because that's the way that you originally learned about them. I don't think it's very possible in your CSCI 40 class, besides maybe like a few passing sentences from your professor, they might have said something like, oh yeah, these were made on the heap, but you didn't really get into it. You didn't think of vectors in that way. A vector to you in CSCI 40 was just like something I can call pushback on and go to @0 and get the size, and it plays nicely with all of those commands that I ask it to do, right? That's all a vector was to us back then. I want to teach you how to build them, but I also want to go back to that original idea of just like, okay, a vector was something that responded to pushback, something that responded to size. So let's try to kill all of those birds with the same stone, and we'll start with the high level stuff. All right, so let's talk about data structures and algorithms together. All right, so this is pretty much the topic of this class in a nutshell. It's part of the name, right? This is a data structures class. So let's learn a little bit. So what an algorithm is, let's remind ourselves. An algorithm is just a sequence of steps. It's a recipe. It describes a sequence of steps to solve a problem. For us, it's a computational problem, of course, or perform some sort of calculation to like get an answer. And so yeah, we've learned how to make our own algorithms by now. It's been fun. And we want to know which algorithms are better than others, because there's a bunch of different ways to do the same job, right? There's a bunch of different recipes to build the final product, and some of them might be better in some way. So we can ask about then the complexity of our programs. What's the computational complexity is the fancy term. And what that means is you can ask about the resources. How many resources are we using? How much of something that we care about are we using when we run our program? All right. So the two ones that we care about, the two kinds of complexity that we really care a lot about in this class, there are other kinds, but these are the main ones that we study, at least right now. Complexity. We care about how long it takes to run the program and how much memory our programs use. So there's something called space complexity that you can try to measure, and then time complexity that you can also try to measure. All right, and time is money, so time is usually the most important. All right, so yeah, because we only have so much memory in our programs. We can't, like, if we have 16 gigs of RAM in our machine, we can't make like 16 billion and one ints, because we have to leave room for the operating system too. So that's just never going to work out. So we only have so much memory to do our programs, inside of our programs to do our work. And we also only have so much time to wait for our programs to be done. Like if you had a really good algorithm, but it took 50 years to run, it's a useless algorithm, right? So we care a lot about measuring the space and time complexities of our programs, and those kind of lead into the idea of algorithm efficiency. That's kind of the study of all of that, right? The efficiency of your algorithm is you finding its computational complexity and writing that down, and people being like, oh, this one's better than this one. All right, we're going to learn how to do that analysis, okay? And yeah, data structures in general, and I want to talk about a new term called ADTs. A data structure is kind of you making a struct. It's you arranging memory inside of a program, okay? A data structure, again, like a textbook kind of definition of that would be, it's a way of organizing, storing, performing operations on your data. And so it's like, I want to put these ints together. I want to put this string, this int, and this double together in this struct or something, all right? When you're making your own data structures, you know exactly what the memory looks like, all right? So it's very concrete. Think like I'm making a bunch of arrays. I'm making a bunch of things, all right? So think array, because array is, you know exactly what an array looks like in memory, right? I know that if it's an array of ints, it has a starting address, it's taking up contiguous space, and I can go to any of those indices, all right? I know exactly what the memory looks like. That's what a data structure is. It's how I've arranged my memory, okay? An ADT, on the other hand, is kind of the opposite. An ADT is a new thing to CSCI 41. It is called, it's short for abstract data type. And what that is you making a type, kind of think of it like a class. A data type is like something you can, it's got operations. It's defined in terms of what it does. An ADT is very abstract and weird, and so I need to tell you more about it, of course. But all an abstract data type is it's some kind of type that's defined in terms of what you can do to it. and you don't know what the memory looks like. You don't care how it's implemented. You don't even maybe know how it's implemented. You just know what you can do to it, and that's the vector idea. So arrays versus vectors. So think of like array is my data structure. It's a data structure. I know exactly what the memory looks like for arrays, but back in CSCI 40, maybe for like most of it, if because maybe you did get into this, I'm not sure, but a vector, we just thought of a vector as like something that can respond to pushback and at and size, and we didn't really know or care how it did all those things. You see the difference? It's kind of philosophical. An abstract data type is defined in terms of what you can do to it. You could store a vector as maybe like a weird string if you wanted to, but secretly a vector is an array that's made on the heap. But a data structure is something concrete. You know exactly what the memory looks like. You can zoom in on it. You know that the int is over here, the string is over here, all right? But for an ADT, we don't even know what's underlying this data type. I don't know what the vector is defined in terms of. It could be something weird. It could just be like a bunch of int variables. Could be an array of ints. But as long as it responds to pushback and at and size in the way that I'm expecting, I'm fine. I'm fine with that. So it's abstract. It's defined in terms of what you can do to it. Defined in terms of its operations. All right. So array versus vector is the good thought that I want you to have in your head when you see these two terms. And yeah, so we care about like matching ADTs. Like we have this idea of what we want. We want to match it to some data structures that will provide us the most efficient ways of implementing those data types. All right, if that made enough sense, that's pretty much exactly where we're going in this class. All right, and so there's a lot of overlap here, but I hope you can kind of see the philosophical difference. Okay, like I know what the memory looks like versus I don't care what the memory looks like. I just know what I can do. All right, so there are certain things that you can do on like the very common things you want to do to like data structures and ADTs together. Like think like I can do the same things to vectors and arrays, but I didn't really care about how the vectors were implemented. I want to be able to know how to access a piece of this data type, of this data structure. I want to know how to like update a piece of this. I want to go to an index maybe and update a piece. I want to be able to look for something that's in there. Like, hey, is 42 in this data structure? Is this in my vector? Is this in my array? I want to be able to insert a value. Like pushback is a thing. Pushback doesn't really exist with arrays, but you can think of maybe making a heap array and doing something weird that might work. And then remove as well. Like, how do I get rid of a piece of this data type? How do I get rid of a piece of this array, this data structure of mine? Okay, so those operations kind of go hand in hand together, and you want to kind of use data structures to implement data types, abstract data types, ADTs. That is where we're going in this class. I hope that made enough sense. I'm sure it's very vague still. I have to give you more examples, but yeah, here are some slides with that in mind. So yeah, data structures are all about the memory. Like I know exactly what's going on in an array. If you told me the starting address of an array, like, and I knew it held 1, 2, and 3, I know everything about that array. I know exactly what it looks like in memory under the hood. If I take apart the computer, I can go to this address and find the first thing and go to the next. I know exactly where the next address must be, exactly where the third address must be. And I know what's there. There's no questions about what's going on in memory. That's what a data structure is. An ADT looks like this. It's just a black box. That's how we treated a vector in CSCI 40, all right? We're slowly going to learn. We're going to like take away the black and learn what's going on. But it's all about the operations, right? For vectors, maybe we weren't told all of this before. For a vector, it's just kind of like it responds to the way you learned vectors work, right? Hey, a vector, you say push back, and it's like, yeah, for sure, I got you. But as long as it plays the game of being a vector, like, hey, at 3, like that was the last thing I inserted, then as long as it gives me back the thing I put there, it's happy, and I don't care. Okay, so as long as it responds to the questions you ask of it, the messages you send to it, then it is a vector. It doesn't matter what's in here. Does that make sense? It doesn't matter, because it could have been an array, and it usually is, but your vector could sorry, I'm having trouble with my words. I'm very excited about explaining this, obviously. This vector just as easily could have been a string, a weird looking string. So like string S, like maybe this was what the vector's underlying representation was. It could have been like 1, and they could have had commas to separate things. 1, 2, 3, 42. And every time you push back, it like turns that thing into a string and then puts a comma there. This could have been a vector. Does that make sense? You could totally implement a vector like this. It would be really weird and inefficient, but it would work. Isn't that crazy? That's really odd and really cool and really philosophical. All right, so data structure. I know exactly what's going on. ADT is just a black box. It responds to my commands. It's defined in terms of its operations. So that's an abstract data type. It's very abstract, okay? So very odd, I know. With more examples in time, we'll get used to this, all right? So more philosophy on a slide. Just again, the idea of a vector isn't that there's an array inside of it that was on the heap, because that's what's really happening. We don't know. It could have been this weird looking string, right? It could have been a linked list, for example, if you've learned about that in your CSCI 40 class. You could have used another data structure to implement your vector. We don't care what's going on under the hood of an ADT, as long as it responds to the things, all right? As long as it responds to the things. This is like a famous picture, a famous painting that has the same idea behind it, if you've seen it before. Yeah, it doesn't matter that a vector is made of a array deep down. What matters for a vector, what makes a vector, is that you can give it, you can ask of it vector-like things. You can say, hey, I want to push back to you. Give me the thing at this index. Give me the size of you right now. And it plays the game of being a vector correctly. That's what it means to be a vector, all right? The underlying data, the data structures that are deep down in there, the things that we can like get a handle on, that know what the memory looks like, they don't really matter as long as a vector responds in the way that we want it to, all right? So yeah, an abstract data type is just an idea of what we want in our program. It's just an idea. It's a list of things that we want to be able to do, all right? Whereas a data structure is concrete. I can zoom in on it. I know what the memory looks like, and you can use it to implement an ADT. That's the full story. Do you kind of see where we're going with it? That's what it means. That's the difference. So a data structure is something concrete that you can use to implement an ADT, and there are many options for data structures to make vectors out of. There's one normal one. There's the arrays on the heap, but there's other ways too. Okay, so that's the difference. That's abstract data types in a nutshell. And the moral of this story, if you've taken nothing else away from these slides, is that abstract data types, we implement them using data structures. All right, and it's your job in this class to learn enough to use the right ones. Okay, that's where we're going. And so just to get some practice with that, like let's build a data type. All right, let's have you build an abstract data type together, and let's figure this out. All right, so try to pause the video after I explain all of this. Try to come up with a definition for an abstract data type that represents bank accounts. So like a class. Think of this as like a class that represents bank accounts, and kind of come up with a list of what you want to have in this abstract data type. How do you want to interact with a bank account? So what operations should be there? All right, so think of that. Come up with a list of like what should a bank account be able to do. That's the first step. And then try to think about like what data structures are you going to put inside of your bank account class? Like what would be the private member variables then that you're going to use to implement it? Because you see that those are two separate things. You could make the same bank account operations with different data structures, but there's usually one that sounds about right for the thing at hand, okay? So try to think about that and get as fancy as you can while you want to pause the video. Like you can think about credit cards and like interest rates and loans and things. That's totally fine. But it's a good thing to practice. Try to figure out the difference, right? Try to see the difference. Give me a list of operations. That's the ADT part. And then the data structures would be used to implement the ADT. Okay. So yeah, give that a try. And yeah, so here's my ideas. Bank account. Every time we make a bank account object, what do I want in there? Well, it depends on who's paying you to build this type, but I think that a normal thing we want to be able to do to a bank account is like deposit money, right? Deposit. We should be able to respond to the deposit command for sure. Maybe transfer between accounts, like maybe it's gonna transfer, if I can spell that right. Transfer values between accounts, withdraw into cash, maybe from an ATM. Who cares about how they're implemented? I just want to be able to do these things. That's what it means to be an ADT. Withdraw, Maybe we want to be able to look at our balance, right? Without like checking anything, like I log into my app, get the balance of all your accounts. Maybe it takes the account number. And then like if there's loans involved and you didn't pay them all in a month, then you got to like apply the interest to whichever loan accounts you need that on. And so like that's the ADT, maybe. You can think of fancier things. But then like when I make a bank account object, the data structure is deep down, like what do I put there? And just like an int, it could be a data structure. A double is a data structure, that's fine. So here are some ideas, all right, for like data structures that we could use to implement bank accounts that could like handle these things. So let's say that there's maybe only one account. Let's say there's just a checking account for your bank account. And it's just like, you can have one of the data structures could be like a double that is your current balance of your account. Actually, if you've learned about doubles enough in your CSCI 40 class, you might know that certain numbers are not perfectly representable in double form. Like you cannot very easily represent like 10 cents as a double, because like 0.1 as a double is like a repeating fraction secretly. And so what a lot of banks do is they don't store your balance as a double with like decimal amounts of cents. They actually store your balance usually as integers, just how many pennies rather than how many dollars. So that's kind of neat. And that's one way to do it. And then you could store like the rate if this was a credit card account that apply interest deals with. And maybe you want to look at your transaction history. That could be a vector, right? A vector of like every transaction, whatever that type is. You can make a transaction struct. Like, what is my transaction history? Because you usually want to look at that to make sure nobody stole your card and did something weird. And that could be a vector of transactions. And so these are the kinds of data structures that you could build that let these things happen, right? But you have many options for data structures. To be a bank account doesn't mean that, oh, the balance was an int versus the balance was a double. To be a bank account just means like I can deposit and transfer. Do you see it? So that's the difference. And I hope you can kind of, as I say it more, right? It's hard to explain, of course, because it's a new topic. But the more I talk about it, I hope that it's making more sense in your brain. And yeah, with that in mind, I want to teach you how to make vectors. All right. I've told you that vectors are secretly dynamically allocated arrays. And now it's time, right? Now it's time to shine. Let's actually, we know what a vector is. You know, it's like it does pushback, it does size, it does dot at. How do you build a vector? How do you build all the things we want to be able to do? So let's start with the ADT. This is going to be a lab for you, okay? So what do we want to do to a vector? I want to be able to push back a value. Let's do a vector of just integers. Let's make that our thing. So I want to be able to push back a value, a new value to my vector. That adds an element to the idea of the end of it, increasing the size by 1. That's what it means to push back, all right? But we can implement this in many different ways. This is the abstract data type, okay? Size just should give me the current size of the vector, how many things I placed into it. And we're going to do capital vectors in our lab because the lowercase one is already taken, of course, all right? And yeah, you want to be able to go to an index, do a dot at, that should exist to get the element back. And then, yeah, those are the operations I want to be able to hold, to have vectors do. That's pretty much what it means to be a vector. And then there's implementation decisions and data structures. Like here's the line, right? So here's kind of a vague line that separates the two because this is kind of what we want to do. This is a design decision that didn't have to be like this. So vectors, let's have them start out empty, but with room to hold one value. All right, with room to hold one value. We don't have to do it this way, but like this is the way I'm going to ask you to implement it. All right, in this class. So when we make a vector, we're going to make our own class that represents a vector. It's going to have some things inside of it. It's going to have some member variables, and one of those things is an array on the heap. So like here's the heap. It's going to have an array on the heap that holds capable of holding one thing that we haven't used it yet. All right, but we haven't used it yet. That's what a vector is going to start out as. That's how we're going to implement our constructor for vectors. Does that make enough sense? We didn't have to do it this way. We could start out empty with nothing on the heap. That's fine, but let's have room because usually the point of making a vector is you want to put something in there. So at least one thing. So let's make it easy memory-wise. Let's just have it ready to go. And the way that you're going to do that is you're going to set your R member variable. That's supposed to be R. You're going to set that member variable, and you're going to say R equals new int on the heap, like a new vector, a new array on the heap of just size 1. Technically, you could have just said new int, but like this is a better way to do it. All right, just always keep it an array. So that was an implementation decision, but what it means to be a vector is to respond to these commands, all right, and also have some sort of initialization procedure in your constructor, and this is what we want to do in our constructor, all right? So isn't that cool? That's how this is going to work, all right? So let's talk about then how to implement vectors using data structures, using our arrays, all right? And the idea of a vector is when you push back, you have an array deep down. You have an array deep down. When you push back, your array might not have enough size for the new thing. And if there isn't enough size, we better make a brand new array on the heap. All right, and that's why we use the heap, because arrays can't change size, but we can give that illusion by making arrays on the heap. All right, and like making a brand new one and copying things over and making a little bit of extra space. All right, so this is going to be your lab. I'm not going to give you code for this. All right, the job for you in this class is I'm going to draw a lot of pictures, and you're going to copy those pictures into code. That's what you're going to get good at in CSCI 41. And that is just, that's what you have to get ready to do, okay? So I'm here to help you as much as possible, but your goal for this class is to translate my pictures and my words into code, okay? That's really important for your future as a computer scientist and like in industry as like a software engineer. So that's where we're going, all right? So I'm gonna draw a bunch of pictures. So let's say this is what your vector is secretly going to look like. This is what it's going to, well, it's not secret anymore. This is what it's going to look like in terms of data structures. Every time you make a vector on like your own vector, we're gonna say like it's the capital vector class, what's inside of it is going to be some member variables, and we're also going to have an array on the heap, and that's going to be one of them. All right, so here are your private member variables when you make a vector. Every vector is going to have a dynamic array. We're going to call that R. It's going to point into the heap, and it's going to hold whatever we've pushed back. All right, it might have also some empty room for new things that we haven't, like new spaces that we haven't filled yet. But that array is always going to point onto the heap. It's going to be an array of integers that is maybe filled in, like 1, 2, 3, but maybe it's not all the way filled in. Like it's got some room for new things, all right? But sometimes it's full. And when it's full, we're gonna have to like resize, all right? So that's one of the pieces of our vectors. And then we're also gonna store the size, like the current size of our vector. And then we're gonna call that num items. How many things have we actually placed in the vector? As far as the user is concerned, that's just 3 things. All right, so I'll call that num items. Num items, and that's going to be 3. And then the last thing we're going to store, that's just an int. Then one more int is what we're going to need. We're going to need the size of the array in total, the capacity. How many things can it really store right now? And that'll tell us whether we have room to add the next thing. So that's going to be called capacity. So the capacity of this array is 4. It can really hold 4 things, but we've only used 3. Does that kind of make sense? So the user's pushed back 1, 2, and 3. We've resized, and we have a little bit of extra room right now. We've got 4 spaces, 3 things filled in. That's all we need to keep track of vectors and be able to resize things when necessary, okay? And so that's what it means to be a vector. That's like as we've used it a little bit. But when you first make a vector, we're going to do exactly this. We're going to start out empty with room to hold 1 value. In terms of these names and things, like let's say I make a vector v2, what will that look like for us? What will the constructor do? We're going to initialize capacity to 1. It's going to be an array of size 1 on the heap, right? Size capacity, whatever that happens to be, which is 1 right now. And then num items will be 0 because we haven't filled anything in there. Okay, so when you make a vector, this is what the constructor will do. It will make room for 1 element, but that element has not been used yet. It starts out empty. Okay. So capacity, num items, and the array itself. That's what a vector is to us in this class. That's how we're going to choose to implement it. But again, that was just a decision we made. It's the right decision, it's the most efficient one, but it didn't have to be like this. It could have been a weird string, remember? And then here's the array. So, all right, what we do in our constructor for vectors, the way we're going to do it for our lab is we're going to have 0 things initially, but we're going to have room for one thing. So our array on the heap is going to be an array of just one int that we haven't filled in yet. Do you see it? So that's how all of these variables are always going to be kept in check, and we're going to make sure that they're always accurate. So there's nothing the user's placed in our array, but it has room for one thing. Does that make sense? So that's what's going to happen, all right? And now we can talk about how to implement things. Like, how do you implement the .at? If we're going to implement vectors like this, then we just need to go to that index of our secret array, all right? That's the secret. So, so let's say we've got this vector. And I'll talk about these other words here in a second. So here's my vector. It's got a capacity. It's got how many items are in it, num items, how many things that has the user placed into it. And then what's the actual array? And let's say this is what our array looks like right now. The user's pushed back. Let's say the user's pushed back one thing, but we've got room for 3. So the user's placed like a 1 here, and we've got room for a couple more. So num items is 1, capacity is 3. All right, so that's what that will look like in memory. And the idea is if the user comes along and they're like, hey, what's that v at 0? We should give them back 1, right? By using our array and going to that index, because that's where we're storing stuff at the same indices that they're thinking about. That's perfect, right? So we want that to work like that. So you just give back the thing you find. If the user asks you to go to index 0 for your vector, then to you, that means go to that index of the secret array that we're using to implement our vector, okay? That's how that corresponds. But also, though, you know that this syntax should also work, like v at 0. You can also use that syntax to change a piece of your vector. Like, I want to be able to do this. Do you see how that's supposed to go into the array and actually mess with something? So what's going to happen for our at member function? It's going to look like this. It's going to take an index that we want to go to, int index. And the thing it's going to return is not the int that's there, or it's going to return an int reference. Do you see why that's necessary? It's going to return an int reference so we can change the thing. We can actually mess with it. Because if it returned just a normal int, then we don't have a window into that piece of memory anymore. But by returning a reference, then we're good. Okay? So we're going to return a reference to that index of our array. All right? You don't have to actually do anything extra by saying, just if you say in the code, you say return R of this index, as long as the type is an int reference, it will convert that use, that return, into an int reference. All right, so it'll just give back that thing as a reference because you marked what it's going to return as an int reference. So you can just say legitimately return R of index. Okay. So I technically did give you the implementation here, if you remember this, and you come back to this as you're implementing it. You don't have to worry about, like, how do I return an int reference? You don't have to deal with that too much. You just say return R of that index. It will turn it into a reference, as long as you say that's what I promised to return. It will convert it to 1. Okay, so that's perfect, and that's .at. Do you see what it means? So .at is just like, all right, if I'm implementing a vector, I want to go to that the user wants to go to this certain index of the vector. I'm using this array. If they go to an index that they've messed with, then give that back to them, all right? And we can just pretend that they're blissfully unaware of the other indices. They don't know the real capacity, all right? So yeah, that's .at. .size is very easy. Do you see? .size is just a getter because it's num items, that's the size. It's keeping track of how many things has the user placed into this vector. Here it's 1. Here in this example, it's been 3, and it's always num items that's tracking that. The user doesn't care about the capacity. That's our implementation decision stuff. The user just cares how many things do they put into it. So .size is a getter. It returns num items. See that? We're not telling the user secretly what we're doing. We're just having them think like it's just secretly an array of just one thing then, if the size was 1, but really it had room for 2 other things. They don't need to know that. All right? They don't need to know anything about capacity. That's just for us. All the user cares about is num items. How many things did they put in? That's their size for their vector. All right. Do you see the data structure versus ADT stuff happening again? So that's .size, And then of course the hardest one is pushback, because what happens if you run out of room? So let's talk about that, and we'll draw it together, and yeah, we'll give some more examples next time, but this will be where we stop today. Okay, so this is the hard one. So let's say we got a vector, and we know how to implement .at. We know how to implement .size. And so what happens, let's say we've got a vector that looks like this, all right? We've always got a certain capacity. We've got a num items. I'll just abbreviate that. And then we've got an array on the heap. Let's say that our array looks like this right now. We've pushed back, the user's pushed back 1, and there's room right now for another thing. Let's let it get filled. Let's watch it get filled together. So let me make that a little bit bigger actually. Beep. So let's say that we really do, like, the capacity is 2, but the users put 1 thing in, so there's still room. All right. So pushback is easy if we didn't run out of space. So let's call that 2 cases. Let's say that case 1 is the easy one. Like, if there's room, put it there. So let's say we say v dot pushback, and we want to add the number 2. Okay. What needs to happen when we say dot pushback 2? Well, if we can safely add one more thing, if we still have room, if the capacity is bigger than num items, I have another slot in there, all right? Then just do it. So what do we do? Well, our next available slot is conveniently at index 1, which is always going to be our num items if we keep track of that properly. Is that cool? That's neat. So like, go to index num items, that's always the next index that's open. Your size is always the next open index. If there is room, if capacity is bigger than num items, then go to index num items and place that thing there. So that's how that could work. That's case 1. And then of course also implement this as an incrementing of num items. All right. So increment num items, make it 2, because now there's 2 things in that vector. All right. 2 things in the array secretly as well. So now capacity is num items. Now there is no room for anything new. You see that? So that case 1 was the easy one. If there was room, just like go to index num items, add the thing there, increment num items. Yes? That's the algorithm. The other one was the harder one. That's not as easy. So I'll draw a bunch of pictures, but it's going to be, again, your goal to translate my pictures into code. All right? So if we try next to say like v.pushback3, if we try that, then we're going to run into trouble because capacity is not bigger than num items. They're equal. So if we don't have capacity, and we don't right now, here is the secret. Here's what you must do. Here is a valid implementation of vectors. We have to make a new array. There's no room in this one. We cannot extend an existing array on the heap. All we can do is make a new one. Let's make a new array on the heap. You could make it of size capacity plus 1, but then you'd run out of room again if you inserted 2 more things. So to limit the number of times we need to do this, the most efficient way, and you'll learn more about this in a future algorithms class, the most efficient way to implement a vector is when you run out of room, don't make an array on the heap with 1 more element just for the new one, but make a new array on the heap with double your current capacity. So if your capacity used to be 2 and you just ran out of space, then what you should do, the most efficient thing for you to do is make an array of size 4 on the heap. See that? And then store this and like call it like new R or something so that you can copy in what you had before. So go to all the elements. You know that you had 2 of them, right? Because you haven't changed anything yet. Go and copy them all in, get the 1 and the 2, and now you've got garbage in the rest of it, but you've got room now. You see that? Make a new array on the heap with double the capacity, copy all of your original elements into it. So don't get rid of R yet. Don't delete R yet. We have to turn it in. We have to place the old stuff into there. Then you reset capacity, right? Because capacity is now 4. Double it. And then you want to change R out. So R, delete the old one, bring R, say R equals the new thing, right? R equals the new thing. And then you're good to add the next element using all the rules for case 1, because now you do have room again. So now you can play the game of, so this could be like an if statement before you do the case 1 stuff, if that makes sense. Okay. So because then you can do like, okay, go to index num items. That's index 2. That's my next empty space right there. Insert the new thing that I'm asking to be inserted, which is the 3. So 3 is there. And I'm incrementing num items, and I was allowed to do that because 4 was greater than 2. The capacity is now bigger. I'm happy. Okay. Because they were equal, I had to double the array, copy things over. All right. So that is one way to implement pushback. Does that make sense? It's most efficient to double your current capacity because then you won't immediately run out of space with a future insert. So that's why we do it. And you could totally implement it by adding just one element at a time if you wanted to, but that would just like, you'd have to keep copying things a lot more often that way. Okay, so this is the way I'd want you to try it. All right, this is the way I want you to implement it in your lab. And so let's say that, gosh, what's the best way to do this? So let's keep going and try this out some more. So look, we've got a capacity of 4, num items of 3, the array is 1, 2, 3. So this is what the array looks like right now. Let's draw pictures until we understand how this needs to be implemented. So we've got a capacity, we've got a num items, and we've got our array on the heap. All right, so right now, it looks like this. It was 1, 2, 3 question mark, because there were 3 things that the user inserted, but we've got room for 4. So that's what the array looks like right now. So that's what our vector is from the user's perspective. And let's say I add these 2 lines, v.pushback 42 and v.pushback, it's supposed to be a v at least, v.pushback like 55, some other number. And so the 42, that's going to be case 1, right? I'll draw the new stuff for those lines in green. So case 1 is you have room, increment num items, and put the thing there. So num items is always the index of where you place the next thing, because your current size is the next index, right? So 42 is going at index 3, num items, index. Place the 42 there. And I'm allowed to do that because right now num items is smaller than capacity. So 42 is going there, and we're incrementing num items, all right? So that's the answer. And then for pushback 55, we run into case 2. We notice that capacity is equal to num items, and so I need to double the size of my heap array, copy things over, and then I can do case 1, okay? Reset capacity, of course, too. So, okay, make a new array of size 8 this time, right? Always double your capacity. The capacity used to be 4, so make a new array of ints on the heap of size capacity times 2. Or you could reset capacity first and do it that way. Then you just needed to make an array of size capacity. 1, 2, 3, 4, 5, 6, I think that's 8 in theory. 1, 2, 3, 4, 5, 6, 7, 8. I don't trust myself. Okay, and then you bring everything over. Don't delete the old one yet, because you got to bring everything over. You bring over the 1, the 2, the 3, and the 42. And then now you're good to delete the old one. So did I correctly? You have to actually delete it from the heap. I forgot to draw a big X there. So like actually delete it from the heap, get rid of that old one, and then array is now this new one. All right, so don't leak any memory. Really delete that first. And then you're good to, and also remember to do capacity. Capacity is now 8. Num items is 4. And now you're good to do the old stuff. You're good to do the case 1 rules, the case 1 algorithm of just like, okay, now I have room, go to index num items, place the new thing there. So the 55 can go at index 4 because I have room there now. Because 4 is smaller than 8. It's perfect. So I can do case 1 stuff. I'm happy. I can place the 55 there and increment num items to 5. And do you see how this gives the user the illusion that there was always enough room? They don't care what we were doing. As long as we like give them the illusion that this was all happening seamlessly, and it wasn't, it was a lot of work on our end, but to the user, I have an infinitely resizable vector. It holds as many things as I want to give it as efficiently as possible. And that's what an ADT is all about. We have the user interacting with us in terms of what they know they can do, in terms of all these commands they can give us, and we're the ones dealing with all the data structures under the hood and all the different if statements and things and heap memory and member variable resetting to give them the illusion that, like, yeah, we're responding and we're doing it right. Isn't that fun? So I think it's very fascinating, and I hope that you agree. You're definitely in the right place if you like this stuff. This is one way, and this is the standard way to actually implement a vector. And I hope that's cool. I hope you see that like it's not too hard, right? As long as you keep track of all these things, you know how to implement at and size and pushback, and that's all that's all you need to actually make a vector that can hold an infinite number of things, or at least as much as your memory can hold. Okay, and so that's where I want to stop for now. We'll review some more of this next time and go a little bit further, but that's the start of talking about abstract data types and one that we know and love, vectors, and how to implement it using a data structure. All right, using a couple different data structures, the most important one being heap arrays. So yeah, I'll leave you with that. Definitely go back to the code that we talked about, look at my drawings, and let me know if you have any questions, and I will see you next time.